So that covers all of our functional groups. So now we're going to go into the physical properties of molecules. So these physical properties are going to depend on their functional groups which the molecule has, and this is due to intermolecular forces. So intermolecular forces are going to include dipole-dipole interactions, hydrogen bonding, and London dispersion forces, which are otherwise known as either just dispersion forces or van der Waals forces. And so stronger intermolecular forces in a molecule are going to result in decreased solubility in organic solvents, increased melting and boiling points, and increased solubility in water. So we'll look at these in more depth. So we can look at our dispersion forces first. And so this is a bit of a recap from grade 11, so from unit 1 and 2. But basically, just to recap on what you've learnt and as a bit of a reminder, because these are very important, when we discuss dispersion forces, we're talking about the force which exists between all types of molecules. So it's a force which occurs when there's intramolecular non-polar covalent bonding in molecules. And so basically, it's just this weak attraction between every single molecule which holds things together. And so the more electrons which a molecule has, the stronger its dispersion forces are going to be. However, dispersion forces are the weakest of all of the intermolecular forces. So if a molecule only has dispersion forces, it's not going to have very strong intermolecular forces compared with some other molecules which have a lot stronger intermolecular forces. The next one we can look at is dipole-dipole interactions. And so these occur when there's a partial positive and a partial negative dipole which occurs in a molecule, such as HCl, which is shown here. So because of an electronegativity difference between hydrogen and chlorine, there is an attraction of electrons to the chlorine part of the molecule because the chlorine part of the molecule draws the electrons towards it. This leaves the protons towards the hydrogen part of the hydrochloric acid molecule, making this have like what's known as a temporary dipole, where one side of the molecule is temporarily negative and the other side is temporarily positive. And so this means that the hydrogens from the hydrochloric acid molecule are attracted to the chlorines of neighboring hydrochloric acid molecules, forming the dipole-dipole interaction force. And so this is the middle strength of intermolecular forces. It's not the weakest, but it's not the strongest. And obviously this strength does increase with more electrons and greater electronegativity. Now, our strongest of the dipole-dipole interactions is what we know as hydrogen bonding. And so hydrogen bonding is a special type of dipole-dipole interactions, which occurs with molecules which contain a hydrogen bound to either an oxygen, nitrogen, or fluorine atom. And so we commonly see this in water molecules because there's intramolecular polar covalent bonding. And this occurs because there is such great electronegativity difference between hydrogen and oxygen that the oxygen or nitrogen or fluorine, depending on what the atom is, draws electrons towards itself so strongly, creating this very strong temporary positive and temporary negative in the molecules. And so this means that the either oxygen, nitrogen, or fluorine from one atom can be very strongly attracted to the hydrogens from other atoms, forming these strong, what's known as hydrogen bonds between the molecules. And so these are what we know in this syllabus as our strongest intermolecular force. And so when we compare our relative strengths and what they occur between, we can see we've got hydrogen bonding, dipole-dipole interactions, and London dispersion forces. So hydrogen bonding is going to occur between hydrogen atoms and oxygen, fluorine, or nitrogen atoms, and it's going to be the strongest of the dipole-dipole interactions. Then we've got our dipole-dipole interactions, which are just our standard dipole-dipole interactions, and they occur between partially oppositely charged ions, so meaning that ions with a substantial electronegativity difference and so their strength of intermolecular force is going to be reasonably strong, but not as strong as the hydrogen bonding. And then our final one is the dispersion forces, and they occur when there's a temporary or induced dipole, and they have a fairly weak strength. Their strength does increase with larger molecules due to there being more electrons, but they will always be the weakest intermolecular force. And so we can look at the physical properties of organic compounds depending on what their intermolecular forces are. So we've got ionic compounds, and they've got ion-to-ion attraction between the ions, and they've also got London dispersion forces. So we don't really look at ionic compounds in too much depth, but they do have stronger than hydrogen bonds, and so they will have the highest melting and boiling points because they have an ion-to-ion attraction between those particular ions. But we don't really look at those too much. We just need to know that they exist and that the ion-to-ion attraction is stronger than hydrogen bonds. The next one we've got is covalent compounds, which contain hydrogen bonds, so that being an oxygen, nitrogen, or fluorine bonded to a hydrogen in a particular covalent compound. And so this will mean that there will be hydrogen bonds present and London dispersion forces present. There may also just be general dipole-dipole interactions present as well, depending on the particular molecule. And so they will have the second highest melting and boiling point. If we're just considering hydrogen bonds, dipole-dipole interactions, and London dispersion forces, then we would say that they have the highest melting and boiling point. The next one we can look at is the polar covalent compounds. So polar covalent compounds are going to have a dipole-dipole interaction between the dipoles which are created by partially charged ions. So this will be a slight difference in electronegativity, resulting in partial positivity and partial negativity in the molecule. They'll also have London dispersion forces like any other molecule, and so hence they are the next in the rank of height of melting and boiling points. Then finally, we've got our non-polar covalent compounds, and so these don't have any other intermolecular forces other than the London dispersion forces, and so because the dispersion forces are quite weak, they are going to provide these compounds with the lowest melting and boiling points.